This is the physical science lesson video for section 10.1, and as always, if you'll subscribe to my channel, you'll have all my videos for the whole year in one spot. So we're going to go into nuclear chemistry, but just a little bit. We don't go very far in depth. You'll notice that I have some slides I'm going to skip in my PowerPoint. I thought we went more in depth than other teachers have told me that we do. So anything that I skip over, if I do find out later they've included it on the milestones at this point, I will remake the video. Hopefully I won't have to do that though. These have taken a long time to make. So section 10.1 is on radioactivity. So radioactivity is the process in which an unstable atomic nucleus emits charged particles and energy. Any atom containing an unstable nucleus is called a radioactive isotope, or we shorten it to radioisotope for short. During nuclear decay, atoms of one element can change into atoms of a different element altogether. So I know this seems contradictory to what we've talked about before, but anytime we talk about law of conservation of mass or law of conservation of matter, we say mass or matter cannot be created or destroyed in chemical and physical processes. Nuclear processes is a whole different category. So in this case, we can, through nuclear processes, turn atoms of one element into atoms of another element. Now through chemical and physical processes, we cannot do that. Okay, so I wanted to make that clear in the beginning. I don't want you thinking like, wait a minute, when I watched one of the videos from chapter 2, you said this. Okay, nuclear is its own category, so we're going to have kind of a different set of rules happening here. So, types of nuclear radiation. Nuclear radiation is charged particles and energy that are emitted from the nuclei of radioisotopes. Common types of nuclear radiation include alpha particles, beta particles, and gamma rays. Now, there are other ones besides this. These are just the three that we'll talk about in here. So, let's talk about them. So alpha decay. An alpha particle, which is represented by an alpha symbol, is a positively charged particle made up of 2 protons and 2 neutrons, the same as a helium nucleus. So it has 2 protons and 2 neutrons, which means it has a charge of positive 2. Now apparently we didn't need to know this, but it's so short, so I'll just talk about it. It has a positive 2 charge, and the common symbol for the alpha particle is helium, 4/2. 4, of course, being the atomic mass or the mass number, and 2 being the atomic number. So alpha particles are the least penetrating type of nuclear radiation. So in other words, if you have to be exposed to one of them, pick alpha decay or alpha particles, because it's the least penetrating, which means it can penetrate through the lowest amount of objects. And so here is an example. We have a large unstable nucleus. And so if it will emit an alpha particle, which remember an alpha particle is 2 protons and 2 neutrons, then that makes the nucleus slightly smaller and hopefully more stable. Here's an example of it actually happening. Of course, I catch it right as it starts. So we're starting, it has a mass of 239, and so it's unstable, so it releases its alpha particle and it has its mass go down to 235 instead. Okay, and we'll talk about why, but the nucleus being too large is what causes most things to be to release an alpha particle. So this part we apparently don't need to know. This is how you balance equations in nuclear chemistry, but I don't think we're supposed to know that. So beta decay, a beta particle, which is represented by the beta symbol, is an electron emitted by an unstable nucleus. That seems weird, because are electrons in the nucleus? No, they are not. So what is going on here? So in nuclear reactions, a beta particle is written as an E, because it's an electron. Mass is 0, because remember, electrons are so small, they have no mass compared to protons or neutrons. And it has a -1 down here for atomic number, because it's not a proton, it's an electron, which is negative instead of positive. And then it has a charge of -1, because it's an electron. During a beta decay, a neutron decomposes into a proton and an electron. Now, is the proton going to want to stay in the nucleus? Yes, a proton is more than welcome in the nucleus. But is an electron welcome in the nucleus? No. So that electron is projected from the nucleus. The proton stays trapped in the nucleus while the electron is released. Okay, so remember, in beta decay, a neutron breaks apart into a proton and an electron. Okay, and so what happens is you end up changing your atomic number for that one. Alright, so moving on. Again, we don't need to know that, but I will tell you this part. Beta particles are more penetrating than alpha. So in other words, that can penetrate through more different types of materials. And then a gamma ray, which is represented right here, is a penetrating ray of energy emitted by an unstable nucleus. So this one is not a particle. Gamma radiation has no mass and no charge. During gamma radiation, the atomic number and mass number of the atom remain the same, but the energy of the nucleus decreases. It often accompanies alpha or beta decay. So in other words, it's not always one or the other. Sometimes you may have where you release an alpha particle, but you also release some gamma rays. So they can happen together. It doesn't have to be one or the other every single time. So gamma rays are more penetrating than either alpha or beta particles. So let's look at this penetrating thing I've been talking about. So here we have paper. Alpha can't even penetrate the paper. Whereas beta, it can penetrate paper, but aluminum will stop it. Gamma can penetrate paper, it can penetrate aluminum, and only a thick layer of lead will stop gamma radiation. Alright, and so that's why, like, for example, when you go to the dentist and you get x-rays, they put that heavy vest over you. That is packed with lead to help protect you from those x-rays. Remember, all of this can be very damaging to our body, all these high energy waves. So, comparing the radiation. So remember, alpha is represented by our A, or our alpha symbol. The symbol is helium, which is 4/2. The charge is +2, and the mass is 4. Beta, on the other hand, is represented here, and its symbol is E with a 0 and a -1, because it's just an electron. Its charge is -1, and it has a mass of 0, because electrons are so small compared to protons and neutrons, we assume their mass is 0. Gamma is represented here, and so its symbol is the same. And then the charge is 0 and the mass is 0 because, of course, it's just a form of energy. Oh, so we don't do the sample problem because it was about writing equations, and we don't have to do the practice ones or the other practice ones. Boy, I really like doing those too. That's okay though. Alright, so effects of nuclear radiation. So why do we need to watch out for this kind of stuff? So nuclear radiation that occurs naturally in the environment is called background radiation. So even like right now, I'm being exposed to low levels of radiation. It's called background radiation. We can't stop a large nucleus from decaying, and so that just happens in everyday life. When nuclear radiation exceeds background levels, that's when it can start to damage cells and tissues in your body. So nuclear radiation can ionize atoms. And so a lot of times it's seen in birth defects. Like if a parent was exposed to nuclear radiation, if a woman gets pregnant and then has a baby, a lot of times they can end up having birth defects. Now that's not to say everybody who has a birth defect had some sort of nuclear exposure. It's just that is one of the side effects. And again, it's just because it damages the cells and tissues. So how do we know that radiation is occurring? Well, there are devices that can be used to detect it, like a Geiger counter. You may see that on TV, like they'll walk around and they'll take this and like scan, and you'll hear this clicking, and they're in their like suits and everything. That's a Geiger counter. Some places they have a film badge. A film badge, like for example, my father-in-law, he used to work at a nuclear power plant, so he probably had to wear something like this. It's a badge that over time it detects how much radiation you're exposed to. And so once the badge, I think it like changes color or something depending on what kind you have, then you know, oh, I'm getting too overexposed, maybe I need to, work in a different area of the lab for a little while or something like that. So film badges, they're used in some jobs. So, section assessment. How does an element change during nuclear decay? Well, it will release charged particles and energy. The nucleus will release charged particles and energy. I mean, there's lots of ways you can answer this. Sometimes the mass of the element changes. Sometimes the element itself changes. I mean, there's lots of ways to answer that. Number 2, what are 3 types of nuclear radiation? Well, there's alpha, beta, and gamma. Alpha, beta, gamma. Number 3, how are atoms affected by nuclear radiation? Well, again, this one, I don't know, number 1 and 3 are very similar if you ask me. Atoms are affected by nuclear radiation in the fact that their nucleus changes. Let's just say that. So their nucleus can either emit charged particles or emit energy. So the nucleus either emits charged particles or emits energy. Number 4, what devices can be used to detect nuclear radiation? Well, you have the Geiger counters and the film badges. Geiger counters and film badges. Number 5, how do types of nuclear radiation differ in electric charge? Well, alpha particles have a +2 charge. Beta particles, they're an electron, so it's a -1 charge. And gamma rays are not a particle, so it's no charge. Okay, so alpha is +2, beta is -1, and gamma is 0 charge. Number 6, 6, describe the penetrating power of each common type of radiation. Well, let's just list them from least penetrating to most penetrating. Alpha is least penetrating, beta is more penetrating, and gamma is most penetrating. Okay, so alpha is least penetrating, beta is more penetrating, and gamma is most penetrating. So what is background radiation? That is the normal environmental radiation that we're exposed to, so just in the normal environment. Number 8, what is the effect of beta decay on the composition of the nucleus? Well, remember, beta decay, a neutron breaks into an electron and a proton. So in other words, the nucleus would change. There would be one less neutron and one extra proton. And of course, we know that electron is ejected. Okay, so the nucleus changes in the fact that there's one less neutron, but one more proton. All right, and then of course we can skip those two. So I don't think there's any more after this. Let me just double check. Oh, nope. All right, so hopefully now you understand a little bit more about the difference in alpha, beta, gamma radiation and why we don't want to be exposed to nuclear radiation.